Kind of a blah day, huh, with the weather? A little bit? All right, so we're officially a little bit behind in here. We're going to try and, get caught up. Probably not today, but hopefully by the end of the week we'll be caught up. All right, so we were talking about two methods for finding the volumes of solids of revolution, right? We have the method of washers and the method of shells. So I just wanted to kind of remind you quickly what the two versions look like here. If we have a region between two functions sitting in the xy plane, then if we do a washer, in this case, right, we have a rectangle that's vertical, and if we do a washer, we're going to have to wrap it around an axis that would be horizontal, right? And so the washer would look like that, right? That's what our washer is. And so what we do is we find a formula for that volume of that one little slice, and then we add them up with the integral. Now the shell, the only difference between that and the shell is that the shell is going to go around an axis that would be parallel to the rectangle, which means the line of rotation would have to be vertical, and so it would look more like that. So that's just a good image that shows you the difference between a shell and a washer, right? Okay. When we did shells, which is the second one there that I did, when we did shells last class, I only did a shell around the y-axis. That's all I ever did. I need to show you a couple of more examples. So we're going to do that, and then we're going to, yes?
This section is 7.2.
7 point, well, technically, shells is 7.3, technically. Sometimes Cal 2 professors will skip 7.3 and not do shells, but I'm kind of incorporating it all together. I'll give you some homework problems out of 7.3, even though they're not in the schedule. The schedule shows nothing from 7.3. If you look at our schedule, it just says 7.2. So I will give you some in 7.3, just for you to practice. All right, I'm going to leave this monitor up over there, but let me put this away. And then I gave you that problem to take home, right? Trying to find that formula that's due next class. If you have any questions over it, just come see me in my office. All right, so let's what was the region that we were messing with last time? That we did like 3 different problems with this region. What was it? There's one that we rotated. We did shells like x squared and root x? Yeah, let's do that. Thank you. If you have y equals x squared and y equals root x, if you look back in your notes, we had taken that region, we had wrapped it around a bunch of different horizontal lines. So we used shells. What I'd like for us to do is take this region, so same instructions as you have there from last class. Okay, take that region right there, and I want us to rotate it about, not the y-axis. This time what I'm going to do is I'm going to move my axis of rotation. Let's go to the left a little bit. So rotate it about the line. Let's see, a vertical line has an equation x equals a number. So I'm going to say x equals -4. I'm just making up a number there. So I want to take this region, rotate it about this line, and then find the volume. So I'll start with a picture. And we had done this a lot, so we had kind of got this picture down pretty good. This was our root x. This was our x squared. You could say y equals root x, y equals x squared. All right, so there's my region. I want to wrap it around the line x equals -4. So that's over here, right? So here's my axis of rotation. We want to wrap it this way. Rotate it. So my rectangle, it can either be vertical or horizontal here. It's up to me how I want to do it. If I do horizontal, what would I have to do? If I was going to do a horizontal rectangle in here, what would I have to do?
Needs to be converted to x.
Yeah, if you're going to do a rectangle that goes horizontally, these curves have to be functions of y, not functions of x. And so I'd have to solve this for x and solve that for x. And then I could do a rectangle going this way and use which method? Washers or shells? Washers, because I would have a rectangle that is perpendicular to my line of, or axis of rotation. Now, our functions are functions of x, so it seems like it would be better for us if we could leave our rectangle vertically, like this, and then wrap it like that. But now they're parallel, right? The rectangle is parallel to the axis of rotation. So that tells me right now that I'm going to need to use shells. Right? I'm going to stick with this. I like this method because these are already functions of x, so I don't want to mess around trying to get them to be functions of y. Now, if you go back and you look at last class, we had this idea of a shell, and then we cut it, right? We cut it open and laid it out, and we came up with a formula, right, for the shell. And do you remember what that formula was?
2 pi.
Yeah, it was, let me draw it. I'm going to draw it again here. This is what happened when we laid it open. This right here was dx. This right here, from here to here, the height of the rectangle, or the height of this shell, is the same as the height of the rectangle, which is your top function minus your bottom function, right? I'm going to write here, instead of f of x minus g of x, I'm going to write top minus bottom. Okay, that's the top curve, right, which would be this one. In this case, it would be this one, and then the bottom one would be this one. So that's this distance. And then this is the part that's going to be a little bit tricky. When I presented this to you, I told you that this was 2 pi what? X, right? 2 pi x, where x was the radius of the shell. That was the distance from here to here. And that was because we were wrapping it around we were wrapping it around the y-axis in the previous problem. So the distance from here to our rectangle is x. So it made sense that if this is the distance when we wrapped it around y, that would be our radius, right? But for here, that's not our radius, is it? Our radius is actually from the axis of rotation all the way out to the end of the shell, right? So I'm going to call this distance from here all the way here, I'm going to call that r. Now, I believe in my formulas I put down here, let me bring it up. There's that sheet that I showed you all last time. It has a summary of all the formulas on it. Where is that thing? Come on. Where is it? There it is. Yeah, okay, so in my formulas I do call it R. Okay, I call it capital R, but let's follow that formula there. So we'll just go capital R here, okay? So that changes, that means that this distance, right, this right here is our capital R, which means when we laid it out, it was this length was the circumference, which is 2 pi times capital R in this case. So in the first time I ever showed this to you, we wrapped around the y-axis. This was x. That will always be the case if it's the y-axis. But if you move it, your axis of rotation somewhere off the y-axis, this radius is going to be determined by how far you are, right? This r is the distance from the axis of rotation to the shell. And I think I say that right there in the notes. Capital R is the distance from the axis of rotation to the rectangle. And then once you have that, you can put it all together with your formula, right? So the volume of this one piece would be this times this times this, so all of these multiplied together. And then you're going to add them up with the integral. So let me put it right here. So I'm going to take the integral, and I'm going to start, where are we starting, or where does our rectangle start at? They start at this corner right here, which is 0, right? And it stops where these two hit each other, which was 1, which we did already last class. So we know our integral goes from 0 to 1, right? And then when we multiply these three together, right? The 2 pi is a constant, it can come out. Okay, so I'm going to take that out. That's why in the formula you see the 2 pi is out. 2 pi. And did I hit record? I did, right? Yeah, okay. And then I have the r. What's r for us here? What's the distance from here to here? X plus 4. It's a distance, right? Even though this is -4, right? If you measure it with a tape measure, it's going to be a positive distance. So this r here is the x plus 4, right? X plus 4, not just x. It's the x plus this 4. And so that's my r. So that goes here in parentheses. You have to have it in parentheses. That's going to be multiplied times the top function minus the bottom. What's our top function? Root x. Bottom function? X squared. There you go. That's your integral. Hey. All right. Any questions? We're using shells, so we're going to have a 2 pi. The integral goes from where the rectangle starts to where it stops. The first piece is the distance from the axis of rotation to your rectangle. That's your radius. And then you multiply that times the top of the rectangle minus the bottom, right? And then you multiply that times the width of the shell. That's it. It's all put together. Now, I'm not going to go any further, right? This is just the setup. I would probably FOIL this out, because these are all powers of x, right? I'd probably FOIL this, and then just integrate term by term. No questions? Yes?
So you said that we could have used the Washer's method if we converted this whole thing into a function of y. Is it safe to say that if it's a function of x, try to use either method depending on the axis of rotation?
Here's the way I look at it. If you're given functions of x, then the best thing that you could do is, I think the best approach then is that you're going to have a vertical rectangle. Okay, if they're functions of x, that's what you're going to have. So if you're asked to rotate something around this way, use washers. If you're asked to go this way, use shells. Now, what if you're given something where they're functions of y? Well, then that tends to be better for a horizontal rectangle, right? So imagine you have a horizontal rectangle now, right? Then if I ask you to wrap it around something this way, you would want to use shells, because see, it's parallel to the axis of rotation. So I would do shells this way. And then if I went this way some way, it would be washers. So I usually let the functions in the region dictate what method I'm going to use. The great thing about shells is that now we have, if you have a vertical rectangle, you can do it this way or this way. You never have to switch this to a function of y. You just leave it as a function of x and we can still go this way. We couldn't do that with just washers. Any other questions? Yes?
So the difference between that equation and the other one, it was the pi, and then it was the out squared minus in squared. Is that one is just a volume of one slice?
Yeah, so the other formula, right, let me scroll up. The other formula is for washers, right? That's for shells right there. For washers, the formula looks like that. It's pi. Sorry, that's if there are functions of y. Let me go back to a function of x. There we go. So that's the formula right there. So it's pi, integral a to b. So imagine we were going around something this way, like this, okay? Then it would be pi times the integral from 0 to 1. And then what I would have to do is what we did last class, where we had this axis of rotation. We'd have to figure out the distance from the axis of rotation to the outer edge of the rectangle. That would be RO squared. And then the distance from here to here would be Rn. And then square that, subtract, and that's your integral. Yes?
When it's a function of x, is always going to be vertical, and when it's a function of y, we'll always
When you have functions of x, a vertical rectangle makes the most sense, because your top function and bottom functions, well, they're going to be functions, right? If you had functions of y, it wouldn't work that way. So if you had functions of y like this, right, those are functions of y, not functions of x, then it makes most sense to do your rectangle this way, because your your right and left functions are two different functions. If you try and do a vertical rectangle in here, notice that the top and bottom are the same curve, and it won't work, right? Does that make sense to you?
Yeah.
Anything else?
So then what determines if it's a vertical or a horizontal rectangle?
If they're functions of x or functions of y. Yeah, if they're functions of x, you want to go this way. If it's functions of y, you want to go the other way. You're just agreeing. That's a function of y, not a function of x, right? This is a function of y, not a function of x, right? They fail the vertical line test, but they pass horizontal. If you try and draw a vertical rectangle right now, okay, try and draw me a vertical rectangle, let's say right here. The top of this rectangle and the bottom of this rectangle are the same curve. So if you try and do like top minus bottom, you can't because it's the same curve. Does that make sense? This top and this bottom are the same. So you can't do it this way. You have to do it this way. Now, your right curve and your left curve are two different curves. So the horizontal rectangle makes the most sense when you're doing functions of y, vertical rectangles when you're doing functions of x. Let's do this same region. I want to go around a different line, okay? Same problem. Let's go about, so rotate it about, let's go x equals positive 4 this time. So the other side of the region.
Would R just be negative 4 minus x?
That sounds right. That sounds right. Let's draw it though. We've got the region. Okay, root x, x squared, we've done this a lot, right? And we want to rotate this around 4 over here. That's our axis of rotation. And so again, because these are functions of x, a vertical rectangle makes the most sense here. And if I want to rotate around a line that's parallel, then I'm going to use a shell. And if I'm going to use a shell, what I need to know are, let me put the formula back up here. If I want to know what the volume of a shell is, or the volume if I rotate using shells, I'm going to use the integral 2 pi. Let's see if we can set this up. 2 pi. The integral is going to go from 0 to 1 again, because we're going to start at 0, stop at 1. Move that rectangle through, create all these shells. And then I need capital R, right? Which is the distance from the axis of rotation to the shell. That's the distance from, here's our shell, to the axis of rotation. That's capital R, and we need to know what that is. It's not x, right? X goes from the origin to the rectangle. That's always been x, right? So what is r? 4. Well, 4 would be the whole distance, wouldn't it? From here to here, that would be 4.
4 minus x.
It's 4 minus x, right? It's 4 take away x. So if your whole distance, right? If your whole distance, these markers. If the whole distance from here to here is 4, right? And you want to know this distance, then what you're going to do is take that number 4 and subtract that number x. So 4 minus x goes here. And then your top function minus your bottom function. Dx, and you're done. That's it. I mean, we're not going to do that. Or do we all? We're not going to evaluate this. But do you all agree this should give us a different answer than the previous problem, right? If your axis of rotation changes, we're going to have a different shape. It's going to be a different object. So it should have a different volume. Okay. Let's do one final problem, all right? We're going to do one final problem. Let's just stick with this same region. It's going to be a recap pretty much of everything we've done. I'm going to take this region right here, and I want us to rotate it around 6 different lines. And we're going to go fast here, all right? So part A, I want to rotate it around the x-axis. Part B, I want to rotate it around y equals -2, c, y equals, let's go with 1, d, let's go around the y-axis, e, let's go around x equals -7, and f, let's go around x equals 1. Take that region, rotate around those 6 different axes, and just set up these integrals, right? I'm not asking you to evaluate these right now. Just set up all the integrals that would give you the volume of the solid that would be created. So for part A, quick picture here. We're rotating it around the x-axis, right? So our axis of rotation is here. Vertical rectangle makes the most sense, right? So over here on the side, the way I did this is I said, okay, I'm going to take my axis of rotation here, and I need to know this outer distance and this inner distance, right? Oh, I'm using washers, sorry. This is washers. Why am I doing washers? Rectangle is perpendicular to axis of rotation. Perpendicular to axis of rotation, you use a washer. What's the outer radius? It's the distance from the axis of rotation, which happens to be the x-axis, to the top of the function, which is, or top of the rectangle, which is square root of x, and then the inner radius is the distance from the x-axis to the bottom of the rectangle here, which is the x squared function. So I'm going to use my formula. Any questions? Volume will be equal to pi. Integral goes from 0 to 1. That will move my rectangle back and forth, or sorry, from the left edge to the right edge. Then it's the outer radius, which you said was the square root of x, that squared, minus the inner radius, which you said was x squared, but then that squared and then dx. There it is. All right, I'm using that formula right there. How about part B? The only difference between part A and part B is what? Axis of rotation. It used to be the x-axis, right? Now we're going to come down to and draw a line. That's where we're going to rotate. So it looks like this. Here's our region. Right? Our rectangle's in here. We already know this is root x. We know this is x squared. But this time our axis of rotation, here's -2. Our axis of rotation's down here, right? Now, the way that changes things is that when we go over here and we draw our little rectangle, we draw the x-axis, we draw our axis of rotation, our r out is that distance now, right? And our r in is that distance. And that's no longer just root x and x squared, right? What is it? What's the distance from here to here? It's that distance, right? So it's this distance plus another 2. So that should just be root x plus 2. The rest of this should be the same. Pi integral 0 to 1. This should be root x, but we're adding 2. Don't forget, square it. Minus, now the inner radius should be that distance, which is the distance from here to here. That's x squared, but then add 2. I'm going fast because we did these already. Are there any questions, though? Sure? For C, let me do C over here. For C, we have, our picture looks like this. We have our region here, goes like this, root x, x squared. Where's our axis of rotation? Y equals 1. That's actually, that's where they hit each other, right? Don't they hit each other right there at 1 unit up? So our axis of rotation's right here at 1. Our rectangle's in here. So watch what I do when I draw this. I always draw the x-axis. I always draw my rectangle. I always draw my axis of rotation. This is the first problem where our axis of rotation is actually above, right? It's above the rectangle somewhere. RO, the outer radius, is distance from here to here. It's distance from the axis of rotation to the outer edge. And then this is Rn. I'm going to blow that up. Okay, what's that distance from here to here? Well, what do we know? The distance from here to here is what? What's the bottom of that over there? That's x squared, right? And the distance from here all the way would be what? 1. And so if we want the distance from here to here, it's going to be this 1 take away that x squared, right? So the outer radius here is 1 take away x squared, right? The inner radius would be this one right here, right? We want to know what that is. And again, we know the distance from here to here, that's the root of x, and the distance the whole way was 1, so it should be 1 take away root x. Y'all got that? Remember I told you when we were doing all these techniques of integration last time, you know, all the partial fractions and all that? I said what we're going to go to now, most students do better on because it's visual. If you're not getting the visual connection, though, this can be really hard if you're not making the connections. So, you know, get with me. If you're having trouble with this, fortunately, this is like a light bulb. Partial fractions is never really a light bulb that just goes off. It's just you do enough where you start feeling comfortable. This is more like a light bulb. It's like, I see it. Okay, now that I see it, everything's okay. So if you're having trouble seeing it, please get with me. All right, here we go. So we go pi. Integral goes from 0 to 1. Outer radius, which was 1 minus x squared, that squared, minus the inner radius, which was 1 minus the square root of x, that squared, dx. I should have that in parentheses like that. But. All right. This is the volume if you rotate around the x-axis. Rotate around y equals -2, y equals 1. Now, all of those were washers, right? Now we're going to rotate it around lines that are vertical lines, right? And so all these for D, E, and F, these should all be shells. So here's what I'm going to do. I'm going to do one of these. You pick. Which one do you want me to do, D, E, or F? What did I can't tell if you said D or E, both of you.
They said different.
They said different? I couldn't tell.
I'll say F.
You want to do F? I think F's the best one to do. Let's do F. So let me give you the answers. I'm going to give you the answers to D and E, and then you can see if you can get those answers yourself. So D, it's a shell, right? So it's going to be 2 pi. The integral is going to go from 0 to 1. If I'm on the y-axis, then the radius, capital R, I'm using this formula, is if I'm on the y-axis, capital R is just always going to be x. It's the distance from your rectangle to the y-axis. So this will be x. Then it'll be the top function, which was the root x minus x squared dx. For part E, I'm rotating it around a line that's over there, right? Here's the y-axis. It's 7 units that way. So I need to add that much to my radius. So I do x plus 7. It's the only difference between the two. Now, you asked for me to do F, so I'll actually show F. So for F, I can draw my region. My axis of rotation is actually here at 1, isn't it? My rectangle's in here. I'm going to use a shell, right? For shells, I just need to know what top and bottom here, f of x, g of x, I have that already. So really the hardest part is just to figure out what this capital R is, the radius, the distance from the axis of rotation to the rectangle. I know that this is x, right? That's always x. From the y-axis to the rectangle is x. I know the whole distance from here to here was 1. And so the radius should be what? 1 minus x. So the only difference between this for part f is that you have 2 pi integral 0 to 1, 1 minus x, square root of x minus x squared dx. This is the only thing that's changing in these problems, right? It's the only thing that's changing. Yes?
On a test, would it be okay for us, like, if we have it down to just skip to that part?
I'm going to ask you to draw pictures, yeah, on the test. I'm not going to ask you to evaluate the integral. That's the trade-off. You draw me pictures, then you just have to set them up. But yeah, I mean, moving on, like not in this class, but just moving ahead, like in your future math class, if you ever had to do something like this, if you can do it mentally, just kind of see it and know where things, then go for it. You know, that's better. All right, we are going to move on. Yes?
You say there's no shortcut for those, like
There's not a shortcut? What do you mean?
a formula or something to follow?
Well, what I gave you. Well, there's different approaches. I've seen this taught different ways where, well, okay, let me get to this. I think what you're asking is there a way that maybe we could get this formula so that we don't necessarily have to draw the picture, that we can just go straight to something? There's probably something we could do. The reason why I want you to draw the picture is because I want you to understand the geometry of what's happening, because I think that's more important than what we're actually doing. Like for you to understand where things are relative to one another and how we're just adding up all these things, I think that's better for you as a student than to just memorize some formula that you always use. You know what I mean? It's an understanding thing. I was telling my daughter about this. We were driving to school. We were talking. I read this morning that the standardized test that we use for our elementary school students across the nation, 4th grade and 8th grade tests, the scores in math and reading are at the lowest they've ever been. I don't know what test is. Just the national way that they look at things. Huh?
There is no national test.
Whatever they're using as a gauge, it's national. I don't know what the actual instrument was, but they've been doing that testing or this analysis for 40 years, 50 years. It's the lowest it's ever been. Normally there's always been a little bit of an increase, and it's actually down with every demographic, every area of the country. There's not so they're talking about the repercussions of COVID, right? And learning remotely and how that's impacting students. So the point is, I was talking to my daughter about this, and I was like, it's like the quadratic formula, right? You can memorize